All right, welcome everybody, and welcome back to the seminar series that is being co-hosted with CIB, that is the International Council for Research and Innovation in Building and Construction, and also from Purdue University. So welcome back to the seminar series. Today we have Arka Bhattacharyya as our distinguished speaker for today. Let me give a little bit background about Arka. He's currently a doctoral candidate at the Lyell School of Civil Engineering at Purdue University. He earned his undergraduate degree in civil engineering from Jadavpur University in India. Following this, he worked in the Indian construction sector for Larsen & Toubro for 2 years. During this time, he was a member of the project planning and construction team in a bridge construction project in Kolkata, India. During his tenure at Purdue University, Arka has actively participated in various research initiatives, both funded and non-funded. These efforts have resulted in multiple journal publications, conference presentations, and recognition. His research is centered around enhancing community and infrastructure resilience, as we will see in the seminar today, in the face of course, natural hazards. His expertise spans diverse areas, including economic impact assessment, risk analysis, statistical and machine learning models, causal analysis, and systems simulation. Recently, he has been named a Trailblazer in Engineering Fellow by Purdue University's College of Engineering. Arka comes to us today from India. So please welcome Arka Bhattacharyya. Arka, floor is yours.
Thank you. Thank you so much for the introduction. So yeah, as Dr. Hassak mentioned, I'm currently a doctoral candidate at Lyell School of Civil Engineering. And this is the research that we have done in our lab. And this is the research that basically came out of my master thesis. So I named the title of the presentation as Towards Disaster Resilient Electricity Grid, Risk Quantification and Optimal Strategy Planning. So a little bit of background about myself. I'm from, as Dr. Hassak mentioned, I'm from India. I did my undergrad in civil engineering, and then I worked for 2 years in the Indian construction sector. I came to Purdue in 2018 for my master's degree, and I completed my master's in the construction area in 2020. And then I started, my PhD program. I'm currently advised by Dr. Hassak, and my research covers different areas, but the general theme is disaster risk reduction, infrastructure and community resilience planning, and capacity building. As you can understand, that these research questions are often very interdisciplinary. So in my research, I try to implement the principles and concepts of civil engineering. Then, the data, we use large-scale data, so different analytics algorithms and all, economics principle, as well as some systems thinking. So this, as again, I have been involved in multiple funded and non-funded research initiatives. So to give you a few examples, I have done some research on understanding the cascading impact of grid failure. Then we have done a framework. We have developed a framework that can be used for optimal risk reduction, strategy selection. Then we have worked on Purdue Index for construction. Those of you who are in the construction area, you should definitely see that we have an inbuilt index that's that shows what's the current health trajectory of the US construction industry. So it's just like any index, like for S&P 500 or Dow Jones Industrial Index. This is another index that shows the health of the US construction industry. Then we have developed a model that estimated the indirect cost of the winter storm Uri in Texas. Then we have worked on developing vulnerability maps for roads and bridges, equitable access to infrastructure. And my doctoral dissertation focuses on flood risk and flood insurance in the US. So currently in this particular presentation, I'm trying to cover the first two topics that I worked on during my master thesis. So our work on resilience. So first of all, we need to understand what's resilience. So some of you might be a little new to the concepts of resilience. So resilience is basically the ability of a system, community, or a society exposed to hazards. Now the hazards can be natural or man-made. So natural hazards can be hurricanes, severe storms, floods, etc. Man-made hazards like intentional attacks, terrorist attacks, etc. To resist, absorb, and accommodate to and recover from the effects of the hazards in a timely and efficient manner, including through preservation and restoration of its basic essential structures and functions. This is the definition of the United Nations Disaster Risk Reduction, Office of Disaster Risk Reduction. In this particular domain, we have done different works. So for instance, understanding the feasible resilience. Now, resilience is only one part of the picture. You need to understand the feasibility of your planned resilience. Then we have developed models that can understand the economic impacts of different inoperability or perturbation in the infrastructure, cascading impacts of infrastructure failure during natural hazards, optimal project selection framework, restorative capacity planning, and inequity in power outage. So we have done a whole lot of work in this particular area of grid resilience. So I will only show the economic impact assessment and optimal project selection part in this particular presentation. So to give you an introduction about the electricity grid, there are three parts of electricity grid. The first part is where you generate the power. It's called the generation part. Then once you generate the power, it's transmitted through transmission line. And that part is very high voltage electricity. That electricity cannot be used because our, the devices are only capable of using a small voltage. So there is the distribution part. From transmission, you reduce the voltage through transformer, and then as you see around the blocks, you see different poles and transformers. So those are basically the distribution part. Now, this particular grid structure, it often fails during natural hazards. So, and there are multiple causes: the vulnerability, the aging of grid, the increased frequency of natural hazards, and all. So to give you a brief idea, AC recently graded the US electricity grid as C-. So those who are aware of the grading system in the US, you see A, B, C's, and then you see A+, A-, A, and all. So think in that respect, the grid infrastructure in the US is graded as a C-. So if you are an international student and if you get a C- in any course, that course won't be counted in your plan of study. So think of how that gives you an idea of how bad the infrastructure is. And the distribution part is the most vulnerable. And historical records show that 75% of the outages in the US is caused by severe weather-related events. And by severe weather-related events, I mean the hurricanes, severe storms, strong winds, floods, etc. And the irony is, while I'm in India, we are having multiple power outages at different time. So there might be an outage right now in India, and I might get disconnected. So this basically shows some pictures of grid failure during different super storms and hurricanes and all. So there is a website called the Power Outage .us. If you go to that website, you will see the outage map in the US. And if you look at the Florida region, as you are all aware that Florida has been recently struck by a hurricane, and you will see the extent of power outage in different counties in Florida. So the underlying message is that the grid infrastructure is extremely vulnerable to natural hazards. And as they fail, the effect is often prolonged in the sense that it takes a lot of time to restore and recover that failed grid. As you can imagine, if you see a pole like this is broken, it will take a lot of time to clean this mess up and then restore the grid infrastructure. So the research question that we were interested in this particular research is that what's the economic impact of those outages? So we don't know what's the impact of a particular outage would be on the economy, in the sense that we have never imagined that even outage can have an impact on the gross domestic product of a country. So that's what we were interested in. We were interested in quantifying the impact of power outage in terms of the loss of gross domestic product. And the second question is how to plan for risk reduction. Now we all know that we need to strengthen the poles, we need to elevate the substations so that they don't get flooded. if we make the distribution lines undergrounded, then they won't fail that much. But the question is about the feasibility. Can we do all? Of course not, because we have limited budget. You cannot spend a lot of money, or we don't have unlimited financial resources. That's why we need to plan for optimal risk reduction. And that's the framework we wanted to develop in this particular research. So that can be used in planning for optimal risk reduction strategies. Now, this is the basic idea about the economic impact assessment, in the sense that the impact of outage is not limited to the grid industry itself, because infrastructures are interdependent between themselves. For instance, if you look at the water treatment plants, they use electricity. So if the electricity is disrupted, then the production of the water treatment plant will be disrupted. Again, the transportation sector uses electricity. So if the electricity supply gets hampered, the transportation sector will also get affected. And transportation in turn, used by different industries. So those industries will also get affected. So there are second primary impact of natural hazard on the utility sector. And since utilities product, that's the electricity, is used by different industries, so that's the secondary impact. Again, those industries are also providing services and products to other industries. And that's a tertiary impact. Excuse me. So this is the basic idea about the cascading impact, in the sense that the impact of an outage is not just limited to the utility sector itself, but it rather cascades through the economy and affects multiple other industries and infrastructure. And as a result, you see that different other industries are also affected, and their production is also lost. So if you want to quantify the economic impact of an outage, you need to consider the impact on the utility sector as well as the other industries that are dependent on the utility sector. So this is the basic idea about the cascading impact. Now the question is, how do we quantify this inoperability? And by inoperability, I mean the inoperability is defined as the percentage reduction in the production of the utility sector. So for instance, let's say the utility sector in a year produces 100 gigawatt hours of electricity. And due to natural hazard, let's say the production is reduced by 5%. So 5% is the inoperability. Now the same equation, this particular equation that shows inoperability, can be rewritten as the loss in production, which is the as planned production minus reduced level of production, divided by reduced level of production plus loss of production, which is the as planned production. And this, again, in terms of the utility sector, is megawatt hour loss divided by reduced level of production plus megawatt hour loss. So again, this is basically what percentage of your production is affected due to natural hazard. If it's 5%, then the inoperability is 5%. If it's 2%, then it's 2%. So this is the methodology that we used for quantifying the economic impact. So as I explained, we need to understand how different industries are interdependent between themselves, and how the failure of one infrastructure cascades to the economy and affects all other producing sectors. So to do that, what we did was we collected historical data from Bureau of Economic Analysis in the US. They published different tables and different matrices that shows how different industries utilize each other's products. For instance, how transportation sector utilizes electricity, again, how utility sector uses transportation sector, and so on. So we collected that data for 23 years between 1997 and 2019. And we use that data in a method, this is an econometric method called input-output analysis. So in this particular method, these two tables are used, and these two tables, these are basically matrices. So they are manipulated in a sense in different ways. And the outcome of that is how different industries are interrelated between themselves. It gives us different coefficients, and those coefficients show how different industries are interdependent between themselves. Once we have that inter-industry relationships, we calculated the impact of 1% inoperability in the utility sector. So by 1% inoperability, I mean 1% reduction of production and how that will affect all other industries in the economy and cascade. We wanted to quantify the cascading impact. And this is done for each year. So 1%, the effect of 1% inoperability in the year 1997, then 1998, until 2019. So for 23 years, we calculated the economic loss. Then we used those losses in a Monte Carlo simulation and to calculate the 1% inoperability in 2019 dollars. And we have conducted several cross-validation and sensitivity analysis to prove the robustness of this particular model. So this is again another picture that shows how the inoperability is calculated. So we start with, as I showed in that particular figure, that we start with the initial impact on the utility sector because that's what we want to measure. And so therefore 1% inoperability, it starts with 1% inoperability. And then we use those matrices that shows how different industries are interrelated between themselves. And because 1% is the reduction, the supply to other industries get reduced by 1%. And as a result, you can see the numbers 0.99, that's 99%. Then we use these matrices and vectors in different equations to come up with the inoperability in all other producing sector. So just, it's very difficult to explain in a short time how this goes on, this particular, the calculation. But the summary is that the initial vector had all zero values except for one, and the final vector had all non-zero values. So basically the impact of 1% inoperability in one industry cascaded through the economy and affect all producing sectors. And that's why we are seeing all non-zero values in all different industries. And this effect is also cyclic. So once we have this, we will use this particular vector again in this one. And again, this is a cyclic impact, so the cycle will continue. So in our analysis, we assume that the cycle continues till 3, and because there are several reasons. So the average outage duration in such cases is 72 hours. So that's basically 3 days. So we assume that the cycle will continue for 3 times. So the GDP loss assessment model starts with 1% inoperability in the utility sector. Then we derive the inoperability vector. Then we use that inoperability vector in our equation. This is an equation that was developed. This is basically another one of our contributions in this particular research, that we developed this particular equation. And this equation shows what will be the expected GDP loss in different industries in each year. So for each industry, we know the expected GDP loss for 23 years. And those values are calculated in 2019 dollars. And once we know that what will be the expected GDP loss for each industry for 23 years, we can fit each industry to a triangular distribution. And in triangular distribution, you take the mean, median, and the maximum value. So from those 23 values for each year, we know the mean, that is the minimum, the median, which is the median, all know what's median, and the maximum, and we use that in the triangular distribution. Then we simulated the sum of all those triangular distribution through a Monte Carlo simulation, and this figure shows the result of that Monte Carlo simulation. So what we have seen is that the mean value of the Monte Carlo simulation is $11.6 billion, which means that if there is 1% reduction in the production of the US utility sector, the US economy will lose GDP by $11.6 billion. If it's 2%, then it will be twice of this value, which will be like $23.2 billion. If it's 3 times, if it's 3%, then it will be 3 times of this, and so on. So just for 1% reduction in the production, the US economy can lose $11.6 billion of the gross domestic product. In the next step, what we did was we tried to develop this model, or we tried to scale this model to the state level. We also wanted to understand what will be the impact of power outages that are localized to the state. For instance, right now, the impact of Florida, I mean, the outages going on, large-scale outages are going on in Florida. So we wanted to see what will be the impact of that outage in terms of the gross domestic product of that particular state, which is Florida. So we did that, and I mean, that part I have skipped in this particular. The process is very similar. You can definitely look at the the published paper to get hold of that process. But the methodology is similar. We just did a little bit of tweak in the equation, and that resulted in the same. I mean, and we used that to understand what was the expected GDP loss due to the winter storm that happened in 2021 in Texas, and which was basically a huge power outage. And so Texas is very warm, so their grid is not prepared for winter weather. But in February 2021, a huge winter storm struck the state of Texas, and as a result, the grid infrastructure was devastated. Because during winter, you will see that you will have to start your heater to keep your rooms warm, and as a result, the demand was increased. The demand was at such extent that the grid was on the verge of a collapse. So we used our model to understand what was the indirect cost of that particular power outage in terms of loss of the Texas GDP, not the national GDP, but rather the gross domestic product of Texas. And we found that the indirect cost of that particular outage was close to 500 million or $500 million. But I have not kept that part in this particular presentation because it will take a lot of time to explain it again. I rather wanted to show you how this particular result can be utilized in terms of risk reduction or, excuse me, resilience planning. So what we have done in this particular thing is, this particular part of the research is, we tried to understand how different factors contribute to the failure of the grid. And those factors are called risk factors. The hazards are the hurricanes, floods, severe storms, snowstorms, etc. And these hazards trigger different risk factors. Risk factors can be vegetation. So during any storm, you will see a lot of trees falling over the distribution line, and as a result, you will see outages. Again, during flooding, you will see that the substations getting flooded. As a result, you will find outages. If during the high wind, the poles might get broken, that will also cause power outages. So these are the risk factors. So hazards trigger risk factors that causes, and those risk factors cause outage, and that has secondary as well as tertiary impact, as explained previously. So in this particular framework, we proposed a database, which is basically a database format, where we have explained how the utilities need to collect the data so that they can use that particular data in our proposed framework. So MEDs are basically the major event days, which is the days of different natural hazards or the occurrence of natural hazards. And during any MED, you note down which risk factor was triggered. For instance, if during a severe storm, there was vegetation-related failure or not. If there was a vegetation-related failure, you check that box. Then you try to measure what was the megawatt hour loss or the extent of power outage due to that particular risk factor. And if you know the extent of the power generation loss, then you can calculate the inoperability from the previous equation. So through this database format, we are basically calculating different parameters, the occurrence of different risk factors, and what was the impact of that particular risk factor in terms of the total inoperability. Again, to repeat, the inoperability is basically the percentage loss of production during any power outage. And RIs are the risk factors. So the total number of MEDs in a year is, let's assume that it's N. And the total occurrence of a risk factor, let's assume it's summation Ri. So the percentage occurrence of a risk factor I during all these MEDs are basically sum Ri by N. So let's, for an example, let's assume that there was 10 number of major event days in a year. And out of those 10 days, you only witnessed vegetation-related failure for 6 cases. So your percentage occurrence is 60%, 6 by 10. And the average inoperability is the total inoperability due to those 6 events divided by the total number of times that particular risk factor was triggered, which is 6. Again, if let's say the total inoperability due to that vegetation-related failure was 60 megawatt hour, then the average is 10, which is 60 divided by 6. Now, once you collect this data for several years, you can plot the frequency curve, and you can see, or you can expect to find the mean and the standard deviation of those parameters. Now, definitely you cannot control the number of MEDs, which is basically the occurrence of hazards in a year. We cannot control the occurrence of natural hazards. Of course, I mean, some will argue that by controlling the climate change, we can control the occurrence of natural hazards, but it's safe to say that we are on the adaptation and mitigation end rather controlling part. So the things that we can control is how often vegetation-related failures occur and what's the impact of those vegetation-related failure. So that's why these are the factors that we can control rather than the occurrence of natural hazards. Now, the idea is to understand which risk factors are contributing what percentage to the outage. So the total outage is basically caused by all the risk factors, different risk factors at the same time occurring. So during any storm, you will see vegetation-related failures, you will see poles getting broken, you will also find that substations getting flooded. And the total outage is the sum of the impact of these risk factors. So in our model, we quantified the impact of one risk factor as the product of the MED multiplied by the percentage occurrence of a risk factor multiplied by the average inoperability due to a risk factor. As a result, the total inoperability due to all risk factors is the sum of the inoperability due to the individual risk factors. And as if you can recall, in our previous model, we quantified the economic impact for 1% inoperability. Now, if you know the total inoperability due to all the risk factors, you can multiply that with our 1% value, and that will give, for instance, again, for an example, if the inoperability is 2%, we already know the E loss 1%, which was the $11.6 billion. So this part of the equation gives you the inoperability, and this part we have already derived in the previous model. So if you multiply these two, you will get the annual economic impact. So this is how the risk factors contribute to the annual economic impact assessment. Now, for risk quantification, risk is a function of 3 things. So it's a function of scenario, likelihood, and consequence. Now, scenario in this likelihood is basically the probability of occurrence. Consequence is the economic loss that we have already derived. And the scenario is to what extent we are expecting the failure. Now, in our model, since the objective of the model is to understand how different risk reductions can be planned, we made the model flexible so that it can accommodate the risk appetite of the decision makers. And by risk appetite, I mean the design inoperability belongs to which percentage of the observed inoperability. So to give you an example again, is in civil engineering design, we often consider a design load, right? So this is kind of similar. Suppose you see in an average year, in an average case, the inoperability as 1%. But you still want to design your system for, let's say, 0.5% inoperability. that's how you decide your risk appetite. So if you want to design your mod system for 2% inoperability, that's more than the observed value. That will make you very risk averse, and you will belong to very low risk category. But despite knowing that the average inoperability is 1%, if you plan to design your system for, let's say, 0.2% inoperability, that will make you a very risk-taking person, and that you maybe belong to very high risk category. So in our model, that's how we define the scenario. So scenario is basically the risk appetite, which can be very high, high, moderate, low, or very low. And that will determine which percentile you belong to. And suppose the observed inoperability is like 1%, and your design inoperability is 0.8%. So in a normal curve, this is your observed inoperability, and this is your design inoperability. So there is only 34% chance that the expected inoperability or the actual inoperability will be lower than what you are designing for. So that makes you, since the probability is 34%, that makes you high risk appetite person or decision maker. Now the last part of the puzzle is that we need to understand what's the relative proportion of different risk factors. So and that value. Hello, is there any question?
No, go ahead. There was somebody had opened the mic, so that's
okay.
fine.
Yeah, cool. So yeah, I mean, for understanding the relative proportion of different risk factors, what we need to understand is that what percentage of the total inoperability is caused by each risk factor. So if the risk total inoperability is 1%, and through your data collection, you know that vegetation-related failure caused 0.3% of the inoperability, then that makes the relative proportion of the risk factor as 33%. Basically 0.3 divided by 1, which is 33%. If you know that substation flooding caused 0.4% of inoperability, so the relative proportion will be 0.4 by 1, which is 40%. If you know the relative proportion of different risk factors, you can distribute the total inoperability into different risk factors. And once you know that, you can plan for risk reduction. So if you know the if you know the different risk reduction strategies, you can even distribute the risk to those risk reduction strategies. So you start with one point, you start with the total inoperability, you first distribute it to the risk factors, then you further distribute it to the risk reduction strategies. And that can be, a simple mathematics. So if you know the risk for risk factor, let's say it's 10, and if you are planning for 5 risk reduction strategies, you equally distribute that risk to 5 of the strategies. And the benefit for implementing risk reduction is basically derived through a unitary method, which is what was the reduction of the economic costs due to the implementation of one particular strategy. So if you know that within your territory there are vulnerable distribution lines that fails during natural hazard, and if you plan for 40% risk, 40% of them, if you plan for undergrounding for, let's say, 40% of those distribution lines, then you can expect that there won't be vegetation related failure for those 40% of the distribution line, because since that for those 40% of the lines will be undergrounded, there is no risk of trees falling over them. So as a result, the economic loss will be reduced by 40%, and that 40% is your benefit. So for different strategies, you can calculate the benefit, annual benefit. At the same time, you can calculate the construction cost associated with that. You can calculate the operation and maintenance cost. And at the same, lastly, you can calculate the risk associated with your design parameter. So as I explained, if you are designing for a lower than average, that makes you a very high risk person, but your risk is a function of probability and the consequence. And since your probability is low, the risk is low. And this, we have designed it in such a way that as you increase your risk appetite, the the scope of your risk reduction projects increase, because if you are very risk averse, that means you don't want to take risk. As a result, you should do more undergrounding, or you should elevate the substations more, and as a result, the risk of that failure will be low. So that's how we have designed in the framework. That's how we have defined the risk in our framework. Now, once you know the annual benefits for, you can conduct these net present value. You can calculate the net present value of the benefit. You can calculate the net present value of the construction, as well as the operation and maintenance cost, as well as the net present value of the risk. And you must know that for any strategy, the benefit to cost should be more than one. That's something that you need to have that before implementing any strategy. Because if the cost is more than the benefit, there is no point in implementing that particular strategy. So from this particular equation, from BCR, that's the benefit to cost ratio, you can get what will be the minimum scope of one particular strategy that will keep the benefit to cost of that particular strategy more than one. And once you know that, you can use that in an optimization algorithm to find the scope of different strategies. So basically what happens is that you have multiple strategies. You never plan for one strategy. You plan for different strategies. So for instance, you can do selective undergrounding. You can under part of your grid in different places underground. You can keep the grid underground. At the same time, you can reroute the distribution line so that it avoids those frequently failure zones. You can increase the strength of the poles by taking different measures. Lastly, you can elevate the substations by taking different steps. These are different risk reduction strategies. So ideally, you should have a combination of different strategies so that you can achieve maximum benefit. So our objective is to maximize the benefit within a budget constraint that will keep the benefit to cost ratio for each strategy more than one. So you start with the design risk level that determines the risk quantity. Then you distribute that risk into different risk factors as well as the risk reduction strategies. You calculate the benefit to cost analysis, conduct the benefit to cost analysis. By keeping the benefit to cost ratio more than one, you calculate the lower threshold of strategies. Now you know the lower threshold of different strategies, you can use it in the optimization. And the objective function is maximizing the benefit of that's derived from those strategies. And the constraints can be different things. There can be one budget constraint. Now, if the optimization is not feasible, then you can either increase your budget or you can reduce the design risk. That will reduce the lower threshold of different strategies. But if the optimization is feasible, you can still increase the design risk level and design your system for a higher to make it more risk averse. Or you can, just stop the process there and come up with the optimal strategies. I don't think I have time to explain the case study. We have a notional case study. You can find it I will show the research outputs in terms of the journal papers at the end. So you will find this is a very simple notional case study that we have in the paper that basically explains the whole procedure. And if you see the process, it will be very, it's very well explained. So I hope that you will be able to understand how the process works. So you basically, calculate the risk, then again, distribute it in risk factors and risk reduction strategies. Then you identify different strategies, identify the risk associated with it, the unit cost and the operation and maintenance cost. Then you conduct the benefit to cost analysis. You come up with the lower threshold for different strategies. And you see, this is basically what's the lower threshold for different strategies for different risk level. And then you derive the objective function, which is the maximizing the sum of the net present value of benefits for all risk reduction strategies. And that's subjected to multiple constraints. And this, for the notional case study, the budget was, I can assume that the budget was 45 million. This is the objective function. These are the constraints that basically says the benefit to cost must be more than one. Then there are other constraints such as feasibility and the budget constraint. The cost of implementing all the strategies should be less than the budget. that's, you are all in the construction program, so you all know the cost of the project should always be less than the budget, which might not happen in reality, but that's the assumption. And if you solve this particular objective function, you come up with the optimal scope of different strategies, which is this one, that basically maximizes the benefit derived from the implementation of these strategies. And these are the relevant literature. So if you are interested, go ahead and find these. You can find all these papers on Professor Hastak's Google Scholar profile. And yeah, if you might find it interesting. It has a lot of different things that it uses principles of civil engineering, economics, systems thinking, it utilizes data and all. So yeah, these are basically the products of this particular research. And that, I would like to conclude my presentation and open the floor.
Thank you, Arka. That was very nicely done. Let me see if do we have questions from the audience? Please open your mic and ask question directly. Yes, Dave, please go ahead.
Yeah, Arka, I was curious, for the work that's involved here, you identified the multidisciplinary aspects of it. Do you have a sense through maybe inquiries from the papers or citations whether this is having more interest from construction and civil engineering or utility companies or financial entities, insurance or the like, or government regulators?
Yeah, that's a very good question. So what I can say that there was no query from the government regulator, but this particular paper, it got, regardless of the number of citations and all, I have received positive feedback in the sense that there was one company that uses historical data and develops different models for understanding the interdependence and resilience of infrastructure systems. This particular company called One Concern. So they found this particular paper and they contacted me saying that this is something that we have found and we have found this very interesting. So would you be interested in doing a presentation in front of our team so that we can utilize the outcomes of this research? So that was one thing. Then I have recently been approached by one person who's interested, who has given me a very interesting proposition in the sense that he has found these papers that we have, the works that we have done in grid resilience and all. And he was interested in understanding which counties will have power outage from an impending severe storm or hurricane. And they are in the business of generators and all, so that they can focus their advertising in those particular counties. So they wanted me to see that if we can come up with some kind of model that basically can be used to see if a county there will have power outage from an impending storm or not, so that they can focus their advertisement to those counties. So that's the level of interest that I have seen so far, other than the citations and all.
Thanks. That's actually interesting. The marketing or sales aspect that wouldn't have occurred to me. So thanks for mentioning that.
Yeah, cool.
Thanks, Dave. Any other questions? Anyone, please open your mic and yes, Ali, are you getting ready to ask a question?
Hey, Arka.
Go ahead,
Yes, yes. That was a really nice presentation, Arka, and yeah, well done. So I had two questions. So first of all, the interdependency or cascading impact matrix, I think it was denoted as A. Was it, where did you get that cascading impact matrix? So that's the first question. Was it, what was the source for that?
Cool. So in input-output model, the idea is to use, the make tables and the use tables and you do different, matrix manipulation. For instance, that there are multiple steps involved in the sense that you normalize the matrix, you do some kind of adjustment for scraps and all. Then you come up with a normalized make matrix and a normalized use matrix. And then you multiply those two and you come up with a matrix called A matrix. And that matrix basically shows what's the interdependence between different industries. So one particular value, it's a matrix. So you have the rows are also the industries, and the columns are also the industries, and the rows are also the industries. And one particular value of that industry shows how that particular, those industries that are in row and column for that particular value are dependent between themselves. So that's how. So this is basically the interdependence is basically derived from the make and use tables.
Right. So based on historic data, right?
Based on historical data, right?
Okay, awesome. And I also really like the algorithm that you had come up with at the end of the presentation that came up with the optimal strategy for actually reducing the risk. So, and I was wondering if the costs associated with each of those strategies. So, are there any references that you can refer to so to be able to get the cost associated with each mitigation strategy? Like maybe going with underground infrastructure or rerouting. There were some alternatives that you had evaluated in the case study. So,
right.
How did you basically estimate the cost?
Right. So these are from literature. I found that the unit cost, like for undergrounding 1 mile of distribution line, the cost is approximately $1 million. And the operation and maintenance cost is 1.4% of that. So these are from literature. Again, this is a plausible data set. The problem in the utility is that they never share their data. Real data is hardly available. So you have to use plausible and possible or plausible data sets. So that's how we come up with the numbers.
Yeah, perfect. Thank you, Arka.
No problem, man.
Thanks, Ali. Any other questions? Trying to go through the different screens here, but if you have a question, please open your mic and ask directly. So while you're thinking, Arka, you mentioned state impact, but you didn't go into details in doing that. As you mentioned earlier, I think that the 23 years of data was mostly at the national level.
Right.
So bringing it down to the state level, what was the thought process so people can understand the complexity of that?
That's a great question. So there are two assumptions involved. The first one is the nature of interdependence between different industries are same at the national level and the state level. So at the national level, if your transportation sector is dependent on utility, then we are assuming that at the state level, the transportation sector is also depending on the utility. So based on this assumption, the interdependences, the values that we derived at the national level, we use that at the state level. But the thing is, what's different at national level and state level is that the production output of different industries. Because some industries might have large presence in one particular state. For instance, in Texas, oil and gas industry has a huge presence, but other industry might not have that large presence in that particular state. So we need to understand what's the output of different industry in that particular state. And for that, the assumption was the output of an industry is proportional to the employment generated by that industry in that state. So we know the output of that industry at national level. We know the employment generated at the state level. We know the employment generated at the national level. So we use that ratio to come up with the output level at the state. And the interdependence part remaining the same and changing the output. Our equation has the flexibility of using that, and you can come up with the expected GDP loss at the state level. So this is another assumptions.
Yeah. Thanks, Arka. Well, we have about a minute or so left for any other questions.
Hi, Arka.
Yeah,
Hi.
Majid, go ahead.
Yeah, so I have a question regarding the 1% you showed us that contributed to the outage. I was wondering what's the top risk that contributed to that outages from the data used from 97 until like 19?
What was the
What's
question?
the top risks that caused the outage?
I'm sorry, I'm not hearing properly. What's that?
I mean, what are the risks? I mean, what's causing these outages?
Okay, so what are causing these outages?
Yeah.
So in the introductory slides, I showed that historical records show that 75% of the outages are normally caused by severe weather events. So that means hurricanes, that means severe storms, floods, winter storms, and all. So, and I gave a reference. So, if you look at this particular website called poweroutage.us, you will find the outage map, and majority of those outages you will find are localized in the areas which are struck by different natural hazards. So a few days back, there was a hurricane in California and in the West Coast. So you would have seen the majority of the outages are centralized in those areas. Right now, if you look at the power outage map in the US, you will find majority of the outages are located on that particular hurricane's path. So in Florida, in Georgia, and all. So majority of the outages in the US are caused by severe weather events. So and severe weather events trigger different risk factors. So high wind causes trees falling over the distribution lines. Flooding causes, high rainfall causes flooding of substations. You might see poles getting broken and all. So multiple factors that contribute to the power outage.
Mhm.
Did I answer your question?
Yeah, yes. So I have a second question. So the data you used, like all of it was like above ground grid lines, or like are there any like underground grids in that data?
So the data is at macro level. So we don't know whether the outages happened in the underground distribution lines or in the overhead distribution lines or not. That's a limitation. And since we are developing the model at the national scale, it's very difficult to understand. It loses the micro level nuances of different things. So that's one of the limitations.
Yeah, the reason I'm asking, because I wanted to see like would the outages would be more if the grid was above ground or underground. I just want to see if there is like a difference between
the outages will, based on my understanding, what I think the outages will be much lower if the lines were undergrounded, because if the lines are undergrounded, there is no risk of trees falling over them. At the same time, what happens is if the lines are underground, the flooding might cause power outage because there might be some failure in the lines. And often, in construction projects, you see a lot of utilities, and utilities get damaged. I mean, the distribution lines or water lines, those kind of things can also cause power outage if the lines are undergrounded. So you'll have to find a balance between these two. But what you will see is that in urban areas, in densely populated areas, primarily in the downtowns, you'll see the lines are undergrounded because because of aesthetics and many other things.
Yeah. I mean, it's a trade-off. Like if you do it like underground, the cost to maintain that would be higher.
Yeah,
but the risk
very
would
high.
Yeah. Right. Thanks, Arka.
Yeah, thanks, Majid. I think those were really good questions. And of course, there's a trade-off, right? So if you do underground, as you mentioned, that might be quite cost prohibitive, particularly in a city environment where, you might have to disrupt a lot of other things to make that happen. So indeed, there's a trade-off, pros and cons in both directions. But Any other questions before I take the privilege of the last question? Anybody else? All right, well, let me ask the last question then, Arka. So, you went through this extensive research in identifying inoperability and the impact on the economy, and also we discuss about the national and the state level impact. Now, when we talk about predictable hazards, right? So like the tornado belt or the hurricane season and so on. So certain things the states would can already identify, but in your opinion, how should the states and state utilities utilize this research in uh, ex ante preparation for a disaster?
Yeah, that's again a great question. So, in my understanding, I mean, what I have seen is that, or what I feel, is that there is a disconnection between the private utilities and public entities as well as academia. So, what happens in academia might stay in academia, in the sense that that's not really used by the utilities. But I feel that the way utilities can use is the second part of this research, because that's more relevant to them. They can use the database format. They have the data, it's collected in their format. But if they can collect the data, or rather, aggregate the data or clean the data and make it in the way that's suitable for this particular framework, then this particular framework can be very useful in identifying the real strategies, because it's very practical in the sense it considers the construction cost, operation maintenance cost, as well as the benefits associated with the implementation of different strategy. It quantifies the risk and everything. So I feel that the data collection can be the same, but the database format might need to be changed, and that's how the utilities can. The rest is just following the process that I have explained, but the database format must be changed before the utilities can utilize this particular framework.
So just a follow-up question. Do you think that utilities can use this model and this information and the analysis of this model in regulatory process approvals and things like that, if they need to add resilience to their grid? Yeah.
I think that can be done, because in the risk there is a third party's consequence, and that was the whole point, in the sense that why we were interested in GDP, because that attracts, that gets your attention. Once if someone says, if we don't do this, there will be that amount of loss of gross domestic product. So since the risk is quantified and the cost is quantified in terms of gross domestic product, they can show that, yeah, if we keep the grid in this way, it's causing this amount of GDP loss each year. So let us improve the grid, and as a result, we might have to increase the rate, and you need to approve that. Otherwise, we'll lose this amount of gross domestic product every year. And that's how I think they can negotiate with the regulatory authorities.
Yeah. Thanks, Arka. Ali, it looks like you are going to take the mantle for the last question here. So go ahead.
Yeah, thank you. So this discussion raised up a question. So different stakeholders might see benefit and interpret benefits in a different way, right? So usually utility companies are private, and then maybe state and even federal stakeholders are interested in a different set of benefits, right? The GDP, maintaining GDP is one benefit at a higher level, as opposed to maybe financial benefits of the utility company. So do you see a way of incorporating different stakeholders in identifying the optimal strategy? So I think that can be a good addition, I would say.
Yeah, my understanding is that utilities are always interested in capital projects, because by capital project they invest money and they negotiate with the authorities in such a way they expect a hefty return on that money, and that return is generated by increasing the rate the utilities are charging. That's why any capital project needs to be approved through regulatory commissions, because ultimately the cost will be borne by the customers. So in terms of engaging stakeholders, this is again, it's a negotiation in the sense the utilities need to negotiate with the regulatory commission. And that's what I was explaining, that if they can explain to the regulatory commission, the benefit of letting me undertake this particular project is the reduction of the loss of gross domestic product, then the utility regulatory commission, which are the public bodies, may be more interested in approving those initiatives. That's how basically you can establish a collaboration.
Right, perfect. Thanks.
Great, thank you, Ali. Well, I think we have exhausted our time, but does anybody have any pressing questions that Arka can answer now? Okay, I don't see any hands going up or mics opening. So Arka, thank you very much. I think that was a very well presented seminar. Dave, you have a question, or are you just saying thanks?
It's just the clap emoji.
Okay, okay, thank you. Yes, so let's give Arka a big round of applause. I think this was very wonderfully done. Please open your mics and give him a round of applause, please.
Thank you, sir.
Thank you, Arka, and thank you, everybody. Next week also we have a very nice seminar organized, and for the rest of the seminar as well. So you will soon learn about other speakers that would be sharing this platform in the coming weeks. So thank you all.
Thank you. Bye-bye.
Bye.